Okay. Yeah, cool. Thank you for joining us at this hour. We are happy to have you this afternoon to one of our final session on machine learning from Arewa Data Science. Today we have one of our finest mentor, Mustapha Abdullahi, who will give us talk and dive through reinforcement learning. Mustapha, he is our deep learning mentor who recently finished mentoring our deep learning with Python session. And we hope some of you, when you finish this machine learning with data science from RDS, when we open the next session, you'll join. I do hope you will enjoy this session. Mustapha, he recently finished his master's from Queen's Mary University, London. He's also Google DeepMind Fellow for Master. He also finished his bachelor from ABU, and currently he is a doctoral student in Finland, University of, Mustapha maybe will introduce more about that. But without much further ado, I would like to hand over to Mustapha to take us through his lessons, and I hope you'll enjoy and learn more from Mustapha. Thank you very much. Mustapha, over to you.
Okay, thank you very much, sir, for the kind introduction. And yes, so my name is Mustapha Abdullahi, and I think Doctor has done much of the introduction. So I'm currently a PhD student at Aalto University, and my research interest is on reinforcement learning and mixture of experts. So it's still like new to me, but just trying to explore new directions. So in this particular session, I'll be taking you through an introduction to reinforcement learning, and with the hope you become interested in it if it's something new to you, and if you already have experience with it already, just to kind of open more avenues in which you could, maybe more areas in which you could work on or focus on in the future, inshallah. So, but I mean, feel free to stop me anytime. If there's anything you don't understand, you could ask questions on the chat, or you could just unmute yourself and ask questions. It's all good to me. So yes. So this is like more of like the overview of what we'll be doing. And we won't really be going too deep in reinforcement learning. It's just to give you an idea what is reinforcement learning and what problems you could focus on reinforcement learning. So yes, so just to give you a high level overview, and hopefully when you get more interested in it, you could like explore deeper your own self, inshallah.
Mustapha, can you unmute yourself? Mustapha, can you unmute?
Okay.
Okay, yeah.
But
yeah,
like the previous, what I said previously, is it okay?
Or yeah, I muted everyone. So because I hear some people noise, so I muted everyone. So now I think you are okay. You can talk.
Okay.
Yeah.
Okay, thank you very much. So I think we'll just kind of go back a bit to machine learning. So my assumption is you've already gone through like machine learning, you've done some exercises. Hello? And you might have come across like the supervised learning, unsupervised learning. I'll just give you some kind of overview, and so just so that you could know the difference in problem solving approach between like this types of learning approaches and reinforcement learning. So in supervised learning, what you usually have, you have a data set and you have input features that describe some kind of phenomenon, and you have like labels, or you call them, let's say you call them targets. So what you try to do in supervised learning, you try to get a mapping from your features to your labels. So easily you could do either classification or regression, which I assume you might have done one of these tasks. So in classification, what you try to do is you try to, basically classify or kind of bin like different classes into different bins. So you try to get like some distinct, you try to put in like some parts of your data set into like some distinct categories. So that's basically classification. And regression, what you try to do is to either predict a real numbered value. So this, for example, you could look at, let's say you are dealing with either housing and you have some information about some house. It can be bungalow, it can be it can be a flat. So using those particular features, you can predict the price of the house. So that's regression. And the output of that model is like a real valued number. So it can be anything from 0 or maybe negative infinity to infinity. So that is regression. So in supervised learning, in essence, you have like your features and you have like a labels. So you are trying to form a mapping between your features and your labels. So that's supervised learning. Then another type of learning is unsupervised learning. Here, what you only have is just your features. You do not have your labels. So this is typically good in the sense that getting labels is expensive because you might need like a human to give you the label or some kind of additional mechanism to get your labels. So, but only having features, you could easily get to know some distinct groups between your data that you have. So there are various approaches you could use, either K-means, hierarchical clustering, or GMM models. So just to highlight on this, assuming you have some kind of raw data set and you don't know what labels or what is the kind of key description of those data sets, using unsupervised learning, you can be able to cluster your data into groups. So those groups can mean various things. For instance, let's say you are looking at, there is like a shopping complex which sell items. So those items can range from yogurt, maybe drinks, it could be food items, but you have like some data sets. So using this unsupervised learning, you could cluster it into like food items, into washing items, into various categories. You could also cluster them into prices based on like the parameters you send to your unsupervised learning. So yes, so that's majorly it. So here I will introduce you to a more different type of learning mechanism, which is reinforcement learning. And the goal of reinforcement learning is to maximize the reward. And in the very next few slides, you know why that is important. So we have this, what we call reward hypothesis. So what we assume is if you act on something to get the maximum reward, it's enough for you to learn anything you want to learn. So imagine in the case as a human, you act on the real world here. So you perform actions on the real world, and those actions, you get states and rewards. I'll come to a definition also of what states and rewards mean. So let's say you want to make a cup of coffee, and in trying to make a cup of coffee, you need to boil water. So those are like actions. You boil your water and you kind of put in some maybe coffee beans or anything. So you make an action, and the outcome of the action, it's like the reward you get of taking that coffee. So you take like several steps to get the reward you want of making a coffee. So that's like the sequence of reinforcement learning. You take sequential actions, and after every action, you kind of have a representation of what is the outcome of the action. So let's say the very first step, you want to boil water. After boiling water, you could see the water steaming. So that's like a state. That's different from initial when you started. So the water was maybe at room temperature. So those are states. So just so that you know, reinforcement learning is like sequential decision making. So at every point in time, you take an action, and the result of the action, you get like a state and a corresponding rewards. But in some cases, you don't really get the reward immediately. It takes like a span of time in which you could get the rewards. So, but we'll come more into that, and you'll have an understanding how you could deal with those when you get there, inshallah. So just another additional example. So here you could see like a dog biting a ball, and funny enough, you could see like some other different dog trying something different. So why is that? So the initial dog maybe gets some kind of pleasure or reward, like just biting into a dog or fetch a ball or fetching the ball. Then this small other dog here, seeing something around, decides to like kind of take a bite and see what's the outcome for him. So essentially, this is what we call imitation learning, which is like a subcategory of reinforcement learning. You observe, and based on your observation, you take an action. So observing the initial kind of dog taking a bite at something around, then the second dog here at the very top here tries to do something similar. So that's like a very small intro to RL, but we'll go deeper into the formalism. Please feel free to maybe cut me short. And if you have any questions, just ask in the chat. Yes. So I can't see the chat now, but if there's anything, please, Bala, just notify me, inshallah. Yes. So to come into the actual formalism for reinforcement learning, like as I said, you have like an agent. So this agent can be, okay. Yes. So this agent can be anything. It could be your robot, it could be a human, it could be anything. So anything essentially that takes action in an environment. So the agent here performs an action on an environment. So this environment, you could take it as either a simulation or a real world environment. For instance, for us humans, you could take this environment as like the current world in which we live in. So daily or at every basis, you make an action. So that action impacts your environment. So, and you have like kind of two outputs from your environment. The state of your environment changes to a new state here, which we denote as ST+1. Don't bother about the math, and you get a reward. So essentially, your agent performs an action, and it gets like a reward from that action and a new representation of what the environment looks like. So taking this into account, this goes back to your agent, and your agent tries to learn based on like my initial action and the corresponding state and reward. How can I maximize my reward? So if I could perform maximally to get the maximum reward, then I have learned to ultimately like perform well in this environment. I would get like into more examples in which you would see why this is key. Because the assumption is like if you could perform in maybe any environment and learn to perform well in getting rewards. So these rewards can be either positive or negative. So it doesn't need to be like only positive reward. The rewards too can be negative. So imagine if you like you teach a child or you are a parent to a child, when the child does good, you reward him with like anything positive, a candy or anything. When he does bad, you do otherwise. So in trying to reinforce positive behavior, the child learns what is good and tries to do that all the time. But when he does bad and you punishes him or her in the appropriate way, so it knows that this is bad and doesn't kind of carry on with those kind of activities. So that's kind of the central idea. You reward when good and you punish when bad. Then the agents learn to perform like maximally to the best of their ability in this kind of environment. So just to go over some definition, we have what we call states. So states represent an environment. So it's like the numbers or the description to an environment. So for you now, I would say as humans, your states, what you capture your states is with your five senses. Maybe one mainly is the eyes. You have like the nose, the mouth, and let's say the ears and your skin. So with those, you could have like some kind of representation of your environment. So you looking at me through the screen with your eyes, I am kind of the representation of your environment now. So that's what we call a state. State is just any representation of your environment. Then actions, these are what you perform in your environment. And given you perform an action in an environment, you get like some kind of rewards. Your rewards might be immediate or it might be delayed. So it might be immediate in the sense that, let's say you touching an iron rod, so you get like an immediate negative reward at that instant. Or let's say in the case where, let's say you are likely the kind of person that like sugary things or not really, let's say you drink kind of tobacco or drink alcohol. So in the very immediate point, you won't really see the impact of it. But in the very long run, that's where you start to see the negative reward there. So some kind of reward are really delayed in time. So it depends on the environment you are dealing with. Yes, just to kind of go deeper into this. So you have like your action, you have your environment, and you have the rewards. These are like the three major components of RL, but these actions are divided into subcomponents. So your action can be either deterministic here or either stochastic. So in deterministic action, what you have is given given a state, you will always like play the same action all over again. Stochastics means random. There is no pattern to your action. So one example of stochastic, I would say, imagine you're a tennis player and it gets quite windy. No matter how you try to play the ball, it might not go exactly like the direction you go. So the wind influences your direction. That kind of adds like some stochasticity in your action. So another thing is your action can be either discrete or continuous. In discrete action, you have a finite length of actions you could make. So if you are someone that enjoys playing games, so you could find like consoles in which you have like just up, down, left, right, and maybe ABC. So those actions are countable. So they are not infinite. So in continuous action, you deal with continuous values. You could have if you yeah, if you are dealing with some environment that deals with real valued actions, so your actions can range from negative to positive infinity. You could have like several decimal values and anything in between. So those are like continuous actions. So you could see here a continuous action space. You could have like several numbers. It could be like 100 point something. So you have like infinite set of values you could do. And so those are continuous action space. So also just to kind of break down environments, there's several kind of environments you could look at. One environment, you would say it's either episodic or non-episodic. So I just want to give you this key breakdown of the environment just so that when you try to approach a reinforcement learning problem, you know what kind of environment or action you need to do or how you will frame a reinforcement learning problem. So you could have like either an episodic or non-episodic environment. So in episodic environment, you have like some kind of breakdown in your trajectory. So assuming you have an environment which is like a Super Mario game. So what happens in Super Mario games, you have like several levels. So each level doesn't influence the next level, or at the very end, you have the final level in which you are done. So once you finish the first level, so what you do or the actions you do doesn't really affect the next level. So those are like episodic environment. So it's breaking down into kind of stages. The non-episodic environments are environments that span a very long amount of time. So one visible example is like our example as like our lives as humans. So when you start off, arguably it's not breaking down into stages. So when you start off, any action you take will influence you at the very long run. So those are non-episodic environments. So you don't have them like broken into stages. So yes. So some other kind of environment you could look at is either deterministic or stochastic. So in deterministic environment, what happens is whatever action you given into that environment. So like the state doesn't, you know what state to expect from that environment. So once you give in an action, so you know what kind of state you should expect from that environment. But in stochastic environment, it's quite different. So you giving an action, you are not sure what the outcome of that environment might be. So just to go back, imagine you are playing chess and you make a move. So you definitely know what's the outcome of that move. So those are deterministic environments. But in stochastic, which is, for instance, let's say in stochastic environment, one stochastic environment can be maybe poker, or let's say in the real world, let's say you are driving a car. So you could make an action, but you are not sure how your environment let's say the people at the environment will react to those actions. So that makes it very stochastic. It's random in nature. So your action doesn't really necessarily need to give you like a corresponding state that you expect. So just to fast forward, we have also discrete and continuous environment, just similar to like your action space. In discrete environment, you have finite number of number of representations for your outputs. And in continuous, you have like infinite, it can be like an infinite value space. So yes, just, yeah. So the next one is either partial or fully observable environment. In partial environment, you cannot really capture everything in your environment. You cannot see or sense everything in your environment, so it makes it partial. While in fully observable environment, you have every information of what's happening in your environment. So one example in which I just highlighted here is in the game of chess here. So chess, it's fully observable because you could see like the entire gameplay of your opponent, and you could also see like your entire chess pieces, so which makes it fully observable. You have an idea of everything that's happening within that environment, so it's fully observable. But when coming back to partial environment, in partial environment, just like I said, you don't have all the information you need. So one example is us like humans. So imagine now you are in your room, you only know what's happening within your room. So, but the environment extends beyond your room, which is like maybe the next room or the location in which you are. So that's like an example of partially observable environment. So you only have a limited view of what's happening in that environment, but still, even with that limited view, you could work on that information to get the maximum reward. Yes. Then the final kind of environment in which you could face is either single agent environment or multi-agent environment. So in a single agent environment, you have one actor trying to navigate the environment and making decisions in that environment. But in multi-agent environment here, what you do, you have multiple agents or multiple agents that are trying to get this, they are trying to get like reward in the environment. So in single agent environment, it's relatively easy. It's just one person making the decisions. But in multi-agent environment, it becomes quite complicated, in which you have to either collaborate or find a way out to maximize like the rewards of all agents. So yeah. So just to re-emphasize things, just looking down at these chess pieces. So like I said, it's non-episodic because when you look at it, it's not divided into stages. So you have one entire kind of chess game going like all over. And yeah, so what happens in why it's non-episodic is any action you make influence like your rewards in the coming steps in your chess environment. So it's deterministic because what? It's deterministic because any action you take, you know the corresponding like next state in which you would get taking that action. It's also discrete. You have like these chess pieces, you have like these blocks. So you have like countable amount of chess blocks of white and black. So that makes it discrete. It's fully observable because you know everything that's happening within those chess environment. So it could be either single agent or multi-agent. In single agent, you could either be playing with a computer. In multi-agent, you might be playing against an opponent. So that's for chess. So I kind of want you to look at this example by the bottom right, in which you have like someone driving a car. So what kind of descriptions can you give this car driving scenario? What environment it is? You can just type out in the chat, please. Let me hear your opinion. Is it episodic? Is it non-episodic? Is it deterministic or stochastic? Is it discrete or continuous? I just want to hear your thoughts and see if we are all like aligned and on the same page. Is it partially observable? Is it fully observable? Is it like a single agent or multi-agent environment? I just want to hear your thoughts. Just feel free. There are no wrong answers. Yes, someone said it's deterministic. Nice one. So just to emphasize, your environment can have multiple different, it doesn't need to be one entirely. You could have like multiple different types. Yes, I think there are some answers going. And Yes. So yeah, I think someone mentioned deterministic. Uh, there is continuous, non-episodic, there's multi-agent, there's partial, there's stochastic, fully observable, nice, there's continuous. Yes, thank you so much. So I'll just go over it again, just so that I think there's one more, there's partial. Yes, I think for the partial, you are 100% correct, because let's say, assuming you are in the car, what you only see, it's maybe what's in front of you or behind you. It's hardly the case, like what's maybe beside you or what's far ahead, really far ahead of you. So, which makes it really partial. So, yes, which makes it partial. So it's non-episodic. It's non-episodic, which is correct, because what happens in you driving a car is any action you take now affects you in the future. Imagine you bump into another car, or you, God forbid, crash the car. So like that stays with you forever. It's not like an episode that kind of cuts off. So it stays with you continuously, like years to come. So that makes it non-episodic. And there's also a mention from Nazir and Khadija for stochastic, which is 100% correct. Because actions you make while driving a car, it's not guaranteed to like get like exactly the same output, because there are several factors that affect you driving a car. Because yeah, there are lots, so it's stochastic, yes. So it's also arguably continuous in nature, because when you just looking just at the speed of the car, so it could be some floating point values of some continuous values. So it's, yes, it's continuous. Then yes, so it's, in general, I would say, so it's arguable, you could say it can be either a single agent environment or multi-agent environment, but arguably it's more of a multi-agent kind, because it's you, and you're not just the only agent acting in this maybe road or environment. There are other people who are acting as agents, trying to also get the maximum reward while driving the car. So it's a multi-agent sentence. So thank you so much for the answers. And yeah, but if you have any questions or doubt, just feel free to let me know. I'll be happy to clarify more. So so yes, is there any question? Okay.
Wanda ya samu ko kuma online all the time. Kai yanzu kana iya ganin amfani da
So just to move forward, we have in RL what we call policy. Remember, I told you you have your environment, and you have your environment, and you take actions in the environment. But how can you take actions in the environment? So one key thing to highlight here is what we call policy. So what we call policy here. So with policy, it defines how you act in an environment. So one maybe simple example of policy is maybe the human brain. So what happens in the human brain? You have like some kind of input. For example, let's say you have some input from the eyes, some kind of imagery, and your brain generates an action for you. So that's, in essence, that's maybe how the policy works. So given a state from the environment, so what action can I take? So policy governs how you act in the environment. So in humans, you could see that policy is largely based on our experience, which you will come to see is closely related to RL. So once you've gathered tremendous amount of experience, or even not, even as little as you can, you could be able to take actions based on those experience you have gathered. So what determines those actions you take is a policy. So imagine seeing a very maybe strange dog like coming towards you or biting at you. You know what to expect. So your brain tells you to run as much as possible. So yeah, so like that's how like the policy works based on what you've learned on the environment. So how can you act in this environment? So this is so imagine this environment in which you have a rat trying to find cheese. So there are several actions in which, or just four actions in which you could either go up, you could go sideways. So what the mice have learned or tries to learn with time is, how can I move along this environment here to get the maximum reward. So, but be mindful here, you have cheese, which is good. You have cheese here, which is good. But here you have like poison, which is really bad. So once you take this poison, like everything ends. And you have this tremendous amount of like larger cheese, in which once you get it, it's much more better than uh, this smaller amount of cheese in which you have here. So the mice have to learn a policy in which he would be able to navigate this environment effectively to gain the maximum rewards. So how can he learn that? So that's where reinforcement learning comes in. Like I said, it's sequential decision making. At every step, you take decisions, and based on your decisions, how can you maximize those rewards? So if you could maximize your rewards in any environment, so you have solved that environment, and let's say you get into a similar environment, you would be able to perform really well in that environment. So that's the idea of RL. So how can we formalize this? So don't bother about the maths. I would just explain it like little by little for you. If you don't get it, that's fine. So we can go back over it anytime. So, yes, so we can go back over it anytime. So like I said, like the key notion of reinforcement learning is how can you maximize your reward? So at every point in time, once you take an action, you get a reward. So imagine you sum up all that rewards you get after making each and every action all through your environment. So once you sum that up, it's what you simply call return. So at the end of the day, the return you get is how well the agent has performed in this environment. So this is like a formalism in which you could calculate like the return at every step. So here you have like the reward at the very first step. Let's say step one. Here you have step two. And this formalism here, it's like a simple simplification of all the rewards you could get. This is just the summation sign here. But you have this special term here, which is called like the discount factor. So discount factor emphasizes how much you should prioritize like future rewards. So it ranges between the value of 0 and 1. So if you have the value of 0, imagine you have the value of 0 in this particular equation. So if you have the value of 0 in this particular equation, so everything here, if you have, let's say, let gamma or lambda here equal to 0, so everything here becomes 0. So your return basically becomes like your current reward at that particular time step. So that means what you only care about is you want to maximize your current reward. You don't care what happens in the future. So what you want is like the maximum satisfaction at this particular time. So that's your reward. But let's look at like the very far end where your gamma here is equal to 1. So your return becomes something like RT plus 1 plus RT plus 2. Like everything is equally weighted. So in that particular sense, what you are telling your RL agent or what your RL agent is doing is, I care about this reward and I equally care about the next reward I will take in my next time step. So everything is equally weighted. So one key example I might give to you is, yes, I mean, going back to examples of humans. So what we try to do is, we know like the current reward is important, but we always look towards the future. So imagine eating like cabbages or maybe, God forbid, taking tobacco. So when you take cabbages, it might not give you the reward you want currently, but in the very future time steps, it will be healthy to your body. But taking tobacco or maybe anything negative, let's say maybe something sugary or maybe alcohol, just an example. So what happens? You get the immediate satisfaction now, which maybe might be beneficial to you, but in the very long run, what happens might not actually be beneficial to you. So that's how like discount factor helps. So when your discount factor is 0, you are very myopic. What you care about like currently is just like the current stage, your current satisfaction. So when you have a discount factor that is 1, so you really care about the future. So any reward, you want to maximize your reward at every point in time. So yeah, so these are kind of settings in which, like hyperparameters in which you would have to key in to your RL agent when you try to train your RL agent. So yeah. So, and what is important about setting this reward factor, maybe to some value in between 0 and 1, if you set it to 1, it's easy for your total return to get to infinity. And imagine you have infinite reward or infinite satisfaction. So you would always, so it's more of like your agent would be the, your agent has overfit to some kind of satisfactory level. So your agent won't really bother to kind of explore new avenues in their environment. So you will see how this exploration and exploitation trade-off happens, and we'll just talk briefly into that. So that is like the formalization of reward. So an agent, what you want to do is maximize the total discount, or here we call it discounted reward over some steps of time. Yes. Just if you have any questions and if there is something that is not clear, feel free to draw my attention, or you could definitely type on the chat, inshallah. So this is like the formalization. Don't bother about the math. What I really want you to know here is what you want to do is to maximize your reward at the end of the day. Yes. So like I said, there is a dilemma here in which it's called like the exploitation dilemma. So you could either do two things, like when you have a reinforcement learning agent. So should I explore? Should I see what's out there? And yeah, should I explore as much as possible, or should I exploit? Should I use the knowledge of what I've learned already and just be satisfied with that? So that's the dilemma here. So you could also look at it like in humans. Let's say you have this fancy restaurant in which you enjoy their meal, like you know it's fantastic, and a friend asks you for some suggestions, or you plan to go out with a friend. So should you go with what you already know that is good, or will you try to explore more? So when exploring, there's a likely chance you might see something better, and there is an unlikely chance you might go to a far worse restaurant. So that's like the dilemma in which it happens in humans, and in RL2, it's also the same. So just to give an additional example, so imagine this mice here. So it can perform an action of either going upwards, like to the right, go downwards, or leftwards here. So imagine it takes this action here. So it learns like there's a cheese here. So what happens if you have exploitation? So after learning there's a cheese here, what does the mice do? At every point, time step in time, he comes here just to take this cheese, and he's also always satisfied with this amount of cheese. But imagine if he tries to explore more, he could find this cheese here, which is like a big reward for him. But in the unlikely sense, trying to explore, you would likely go to the poison, and it would mean the end for it. So here you need to learn how to perform these trade-offs. There are various amounts of ways in which you could inject these trade-offs into your RL agent, in which he tries to explore balance exploration and exploitation. Because once you look at it, you can't do all, both explore and exploit at the same time. So you need to choose one. So how could you balance your exploration and exploitation? Yes. So one key way you could do this is what we call epsilon greedy exploration. So what happens in epsilon greedy is, let's say you have, I'll just draw a graph, maybe it might be easier. So at the very beginning here, what you would do is what? Explore. And towards the very end here, you exploit what you've learned. So at the very initial stage here, let's say your agent is very curious what's out there in the environment. So what you try to do is you explore, because like dealing with reinforcement learning, you make several runs and try to see what's the outcome of those runs. And after exploring for a significant amount of time, like you know what's around you, towards the very end, you begin to exploit more. Hey, I've learned like there is like cheese just immediately ahead of me, and next two steps there's poison. I know what to avoid. Then I'm very much more satisfied of what to do, like in the very long run. So you explore first, given like some kind of probability of exploration. You explore, then after some time steps, then you begin to exploit what you've learned based on some kind of probability. So that's like epsilon greedy. So in the very initial stage, you are not greedy. You explore as much as possible. Then after some time step, you become quite greedy. I've gained this knowledge, so I would maybe be able to maximally use the knowledge I've gained and exploit like the environment based on what I've learned. So that's epsilon greedy exploration. So this is one solution to the dilemma of exploration exploitation. So one other way I would just highlight is intrinsic motivation, in which intrinsically you are, or your agent wants to explore by itself. It has this curiosity internally itself. So one example you could look at like babies. So babies are always very curious. So they have that intrinsic kind of motivation or intrinsic seek for reward or to just play around things, to find out things for themselves. So that's one. You could also have this intrinsicity or intrinsic nature in your RL agents. So I guess it's PPO, but I can't remember the particular algorithms that have this RL algorithms that have this particular intrinsic nature. So I'm just saying it out here just so that you know. It's not only epsilon greedy that exists. There are various amount of ways in which you could go about it. Just moving forward. Yes, so there are a number of ways in which you could solve RL reinforcement learning problems. So here I'll just highlight them and just so you understand them. And yeah, so it's all fine. So we have policy-based methods. If you remember what I said about policy, your policy is like a mapping from states to action. So given you could see an environment, so what action should you take next? So that's like policy. So you could, yeah, yes. So you could just have a representation of a state. And from that representation of the state, you get what is the best action you could take at that point in time. So that's like policy-based methods. Then the second one you could look at is value-based methods. So in value-based methods, what you do, you are not learning a mapping from like states to actions. So in value-based methods, you assign a value to states. So one example you could look at is assuming you are the one that like sweet things. So you could able to give values to like things that are sweet. Maybe honey might have the highest value. Then let's say followed by sugar might have a lesser value. Then maybe water might be like 0. Then you have something not so sweet might have like some negative value. So in those particular states, you give like values. So based on those values, you know which to go for. So, but you're not kind of learning from states to action. So you assign each state a value. So based on that value assigned to a state, you could be able to take an action from there. Then finally, there are methods or current methods that mix both of this, policy-based and value-based methods, but this will take longer to explain. So simply what happens here is, one, you have an agent, it uses policy-based methods, a state comes in and generates an action. So after generating an action, you have another different evaluation mechanism, which based on the action you take, it evaluates how well the action you've taken is. So it generates like a kind of value. So that's like a critique. So you have an actor which generates action, and you have a critique which critiques those actions. So when you combine both two, like an actor and a critic, so you would be able to perform well also. So yeah, so these are majorly, this is just introduction. But if you need more information, just definitely reach out and we could talk about it. And yeah, So here, I will briefly introduce Q-learning, just so you understand what it is. So in Q-learning, so initially before Q-learning, what you have is tabular RL. So you remember what I said about policy, the mapping of states to action. So in tabular RL, what you have here is you have some kind of state here, and you have some corresponding like actions that you perform. So given like some state, then you perform like an action here. You could perform maybe any action. So assuming you are looking at the mouse cheese environment, so you perform an action. But when you look at it, it becomes really complicated when you deal with states that are highly complex, especially in like their dimension. So when you deal with environments that have images, so one thing, it's difficult to store these images because you might be dealing with thousands of images, and which itself, like the share number makes it super complicated for you to learn based on this, storing this particular value. And also it could be complex. Images are complex. So apart from images, there are other modalities that are also complex. So using tabular reinforcement learning it becomes quite difficult. So with Q learning, it makes it really easy. So with Q learning, what happens in Q learning here is, instead of having this table, what you have here is more of like a neural network. But just let me know if you have approached neural network, if you've kind of read on it, or if you understand it. If you don't, just feel free. I could always explain anytime. So you have this neural network, which has like several kind of connections. So instead of having this table, your state comes in here into the neural network and it generates an action. Why this is good is, like, a neural network is really compact and it doesn't face the challenges of tabular RL, because tabular RL, when dealing with really large amount of storing of large amount of states, it become really complicated. So with neural networks here, it takes in like the complexities of data. So if you have come across a neural network, you would know like neural network takes in highly complex data and learns representation from those highly complex data. So with this, it simplifies the movement or the mapping from states to action. So this is Q learning. So given a state or a representation of the environment, you pass it into your neural network, then it generates an action for you. So this is Q learning, or essentially what you would say is it generates values of how well the state is, or how well the action you intend to take is. So you could say it generates state value. So it generates how well like it is for you to like move along that state. And from there, you could like make an action based on that. So that is Q learning. So, but there is more to this, but this is like a very simple explanation of Q learning. Yes. So if there are any questions, please feel free to ask. And yes, just going further, 1 minute. So this is one of the works I have done, like perhaps last year or so. It's like using RL in cognitive science. So initial work revolves around like so there was an initial data set of monitoring bumblebees, how they navigate within the environment. But I tried to use reinforcement learning to learn an agent in which would behave similar to these bumblebees. So what happens in that particular case? So you have like this formalism, we said you have an agent which performs an action in that environment. But here I'm dealing with bumblebees, or let's simply say bees. So my agent here is maybe a mechanical bee in this particular sense. So it's a bee which tries to perform an action. So the environment here is you have let's say a nest of flowers, and those particular flowers, some have like some sucrose, some sugar, and there are also other bees here. So it's like a kind of multi-agent settings. So what you could see here is, okay, 1 minute. So what you could see here, you have like the sucrose here, which maybe this bees like. So how can this agent perform an action in this environment such that it could maximize the amount of bees it could get? So the states here are what? The states here are like the position of the flowers, and we call them social cues. Social cues are just relates to maybe the position of other bees in that particular, let's say, flower nest, or yes, that particular flower nest. So why we call them social cues are like when a bee is at one particular flower, we know that there's a likely chance of having like some sugar in that particular sense. So your agent works with that particular data to see what next like flower should it go to. Should I go to like the flower in which there's already a bee? So in there, I'm exploiting like the knowledge I have, because I do know like when I go to where there is an existing bee, so I am almost to some percent, some kind of 98% sure that there would be some sugar available for me to consume. But should I explore more? So this is like the kind of areas in which you could apply reinforcement learning, so that an agent could learn how to behave in an environment to get the maximum reward. And in this particular case, it's like the level of sucrose. So those are like the reward the agent gets. Yeah, so this is just like an example of my past work. And yes. So like we say, you have a policy, and the policy here it might be like a simple brain of the RL agent, and it learns to act on an environment, and based on its actions, it tries to learn what's the best way it could maximize its rewards. So this is just a simple computational model of the existing work. But RL is applied in several areas. So you remember the Q learning in which we talked about? Imagine an agent learning to play in this particular Atari breakout. So the agent, after learning for a couple of hours or minutes, so it becomes like a really good expert at playing game, even far surpassing human level. So you could see how it has learned with time how it should play the game of Atari Breakout. So one key thing you could see is look at where the agent is targeting the ball. It noticed that if it targets towards like these angles here, it would be able to solve the problem more quickly or much more efficiently, doing less tasks available. You could see how it targets like the very end. And so when it targets the very end, the ball could kind of go in here and just continuously makes his problem easy. So this is one of the applications of RL. So we also have the area of robotics.
Look at that. Oh my goodness.
They've got a pretty good kick on them. Good game.
So you have the area of robotics, in which here in DeepMind, what they try to do is have a robot that learns to play soccer, which is really amazing. So there are various amount of there are various
Coming up with these
there are
interesting different
various
strategies,
areas in which
different
you
ways to
could
walk,
approach
different ways to
reinforcement
block.
learning.
And they're doing it. They're scoring over
Yeah, I'll
and
just
over.
skip to the next one. And one other interesting one is the area of using reinforcement learning for biology. So we have this, it's also currently one major problem, prediction of protein folding. The assumption is if you could accurately predict protein folding, you could solve like several problems, and one of which is diseases, or you could be able to break down, let's say, waste. So here, what they try to do also from DeepMind, a bit biased towards DeepMind, so they try to use reinforcement learning to model how they would predict the structure of protein, and they did remarkably well, surpassing like human competitors. So I think one of the first challenges here was 2018, where they submitted their competition. And amazingly, it did really well, surpassing like all those submitted by humans. So yeah, so this is like some of the key applications of RL to the real world, but there are vast other examples in which you could look at. Yeah, so that is majorly it from my talk. I hope you are very much motivated. So if you have any questions, you could just ask me now, or you could reach out to me for a chat anytime. So yeah, so if you have any questions, happy to answer them. So just if you have any questions, you could key in the chat, or you could unmute yourself and ask. So I'll just wait for about a minute or so. Then I would say we'll just yes, we'll just call it a day, inshallah. We'll just wait for about a minute or two. There's a comment by Omar. No, don't worry, I won't shoot you with the gun. It's just a meme, so it's all good. Yes, so I would assume you don't have any questions, but in the case you have any in the future, just feel free to reach out to me if you want to talk about anything or any interesting area you want to work on RL, or in general, maybe AI, machine learning, or graduate studies. So these are some of the resources if you are looking to like go deeper into reinforcement learning that you could really check out. So yeah, so these are majorly it. You have this, they call it Reinforcement Learning Bible by Richard Sutton and Barto. Then you have this course by Deep Reinforcement Learning, which was released, I guess, last year. Then you have this also David Silver lectures. You have them on YouTube. You could also watch them if you are interested, inshallah. So yes, you could have the slides. I will send them to you, or I will send them to Bala, who will forward to you. But maybe please don't share. Maybe it shouldn't be maybe super public, because they are part of the slides that I don't know, because of copyright. So like this image or some other kind of image, which maybe I have not cited, but I'll share the slides with Bala just in case you are you want to explore more. Yes, thank you so much. So yeah, I think that's majorly it. I don't know if doctor is around, inshallah. Yeah, I think doctor is not around. So like, thank you so much for listening. I really appreciate the audience and the answers you gave during the questions. So yeah, so I hope you are motivated and looking forward to see like if we get to meet in a deep learning cohort, or looking forward to see like the works you guys will do in the future, inshallah. Thanks so much. Thank you. Thank you.
Thank you very much, sir.
So nice. Do have a great weekend, inshallah.